seen the earlier discussions about what are the other data may be required and what are the other important parameter and what are the errors that may be associated with the volumetric and the material balance calculations. Okay. In the last class, we have seen that there are some equations and there are some parameters for both the volumetric calculations and the material balance calculation. Okay. And then we have also seen that depending on the calculation and the parameters, there are certain uncertainty which are associated with the both the examples. That means both the calculations. That means whether it is a volumetric or whether it is a material balance calculation. And we have also discussed that there are certain assumptions for considering both the concept. Okay. And if you see the note, you will see there are several tables are given so that you can have some idea about what are the data that you need to know before you are going to estimate the gas in place or the other calculations. Okay. Now we have to keep in mind that as this coal bed methane is very much a natural phenomena. Okay, the coefficient process, the gas trap mechanisms, the porosity, permeability, the total formation, the maturity, everything is totally natural. So we don't have any control on them. Okay, so the uncertainties for changing of the coal properties or changing of the coal composition or the coal rank from one borehole to another borehole or from suppose 100-meter depth to 200-meter depth, this has to be taken into the considerations. Okay, and it is these reasons that if you are going to drill the boreholes for production or for considering the water pumping out, in no two boreholes you will be finding the same parameters of the reservoir or same parameters of the other production criteria. Okay, and there are certain parameters which we have discussed last day, and we have also seen about the certain features of the isotherm graph, which is very important. Okay, so today we'll also continue with this, that when you are having the volumetric calculation or the material balance calculation, how using this calculation, initial calculation, because these two are required to calculate the initial gas in place. Okay, initial gas in place means you're at the time of drilling out or at the time of pumping out, what was the initial reservoir gas content. Okay, that means the gas in place at the particular temperature and the pressure and the particular reservoir properties that is going to be established by the taking out the samples. Okay, borehole samples. So if you are going to analyze and focus the production and forecasting, you know that forecasting is very much essential for those areas where you will be where you are not able to do the borehole or not able to take the samples. As in case of coal reserve estimation in mining cases, you have also seen that we are going to draw the boreholes in some 100 meters or 200-meter intervals, and we are going to assume that there are equal zone of influence, and with that assumptions, and there are some other assumptions like some area calculation, like some inverse distance square method. Okay, we are going to analyze and we are going to estimate the reservoir, total reserve. Okay, now depending on the technique, depending on the what type of assumptions you have chosen, your total gas content or the gas in place as like the coal reserve in the mine is going to be varied. So same thing is going to happen for the CBM reservoirs also. Okay, so if you see the different technique for acquiring the data, there are some different techniques by which you are going to estimate the production. Okay, so what are these techniques? The techniques are, as you can see, the volumetric calculations, what you have studied earlier, the production decline analysis. The production decline analysis has the same graph. That means you are going to analyze the production for some other data, for some other borehole, and you are going to compare and you are going to estimate of the same borehole with having some input data from the earlier cases. Okay, and next is the material balance and the flow equation calculations. Material balance calculation is also you have get some input. that you are going to calculate the total materials before and after the conditions. Okay, and from there you are going to equilibrate the situations, and then you are going to estimate the production. Other than this, there are also simulation methods. Simulation method means there are computerized program. Suppose, as I mentioned, there are 20 parameters. You are just going to change only one parameters, keeping all other 19 parameters same as in earlier cases, and you are going to see the changes and the sensitivity of that particular parameter and how it is going to affect the gas production. Similarly, for second parameter, for third parameter, and for so on. If you change only one parameter at the same time and fix all other 19 parameters, you will be able to see the particular sensitivity of that particular parameter on the coal bed methane production. But then the complexity arises when you are going to analyze 2 or 3 parameters at the same time. Why so? Because some of the parameters are very much interrelated. As you have seen earlier, suppose for gas storage it is the porosity, or for gas production it is the permeability. Now if you are going to see the gas production and you are going to change the permeability, now there are 2 different concepts will be coming. Whether the permeability is the pressure dependent, so you are going to change the pressure and see the variation. Whether you are going to change the permeability concept, permeability value from 5 milliliter C to 50 milliliter C to 1000 milliliter C and so on. Or whether you are going to see the production time, the duration or the life of the borehole, life of the total production data. Or again, you can change the some network. Suppose you have seen that the design output, there is a central borehole, or there may be some 5-point borehole, or there may be some 9-point borehole strata. Okay, and for all the cases, we have seen how those data are, how those design are going to impact the production reservoir. So when you are going to do this acquiring the data and you are going to go for the production forecasting, you have to see that you will be achieving. You can see that that this heading, it is written in, I have also highlighted, by optimizing the completion design. Completion design means the borehole completion design. Okay, that means once you have driven the borehole, you have put the casing, you have set all the parameters, you have total permeability and everything is done. How you are going to operate that borehole, whether you have put the casing, what is the condition of the borehole sides or the borehole wall rock type, what is the drainage pattern and so on. These are all coming in the borehole design. Then optimizing the well spacing, how you are going to put the well spacing, whether there will be overlapping borehole well spacing or it is totally mutually excluded. Mutually excluded means it is not mutually exclusive, means it is not overlapping to other boreholes. Okay, and if it is overlapping, then that means one borehole area is going to influence the production in the other borehole area. Okay, so then it will be very much complex, and you have to take care of the double properties of the 2 different boreholes and 2 different reservoir production data you have to analyze to get the complete analysis of the borehole production. And third is the optimizing simulation design. Simulation design, the way I have mentioned. Okay, we'll discuss everything in detail. After we have done the parameter, we'll go each in detail about the industrial or about the experimental and the simulation purpose. Okay. Now for the volumetric calculations, you know that the volumetric calculation, whatever is based on the total volume analysis, you are going to represent the gas in place in terms of the volume of the gases absorbed in the coal. Okay, so what you can do and where it is applicable, volumetric techniques are very much simple, and it is generally applicable for the new wells where little historical production data is available. Okay, so if you are going to study for the initial borehole data, or if you are going to do the first borehole in that area in the CBM reservoir, so obviously you have no option other than the volumetric analysis, because this is the basic data you are going to get. So you will be taking out the samples, you will be putting them in the dissolvation canister, and you will be going to test for the gas in place, and then you are going to estimate with the total coal reserve. Okay. Then comes the decline curve techniques. The production decline curve techniques, you know, there are 3 different phases. First is the water pumping out with the constant production. and very minimum gas production, but the gas production is going to increase at the end of this first phase, because the gases are going to dissolve. In the second phase, water production is going to reduce and the gas production is going to increase furthermore, and the gas production is going to increase to the peak point. In the third production, the borehole is more or less dewatered, and gas production is also going to reduce, but it is also going to be 4 or 5 times more than the water production, okay, or even a higher ratio. But all of them, the gas production and the water production, are going to reduce with time. Okay, this phase is obviously very lengthy. Okay. Now, the decline curve techniques and material balance calculation generally work well for the producing wells within the established well patterns that have the production profiles with a consistent decline trend. That means, suppose for any area, you have earlier data for the production and you are going to do some other borehole pattern, and then you are going to compare and you are going to estimate that, okay, if there are some other data available, decline data available, so we can compare that and we can fairly predict, or you can imagine that the production is more or less will be the same pattern, more or less will be the same pattern as the earlier cases. Obviously you have to have the data for the production data and for the reservoir data, and doing all those initial study, that will be going to give you the fixed accurate results. Okay. Reservoir simulation is applicable to all stages of the well life. Why reservoir simulation is applicable? Because the reservoir simulation is going to be applied based on the initial reservoir data. So simulation is what? Simulation is that you are going to, just like any computer programming, any software technique, you are going to take some input data, take some fresh data, and you are going to input them and see how those data, and then you are going to vary. Then you are going to iterate the solution, and you are going to see when your least square or the minimum error is going to be established. And so you are going to take that much of minimum error data, accurate data, and the most accurate data. So in case of the Colbert methane, the simulation is going to give you the total trend. Simulation is not a one thing. It is going to give you the analysis based on the varying production data. Okay, and your main target is to get out the coal recovery, the gas recovery. If there is oil, for petroleum in reservoir there is oil, so the same concept will be applicable for the oil also. Obviously there are some property differentiation between the gas and the oil. There are some viscosity trend, there are some other density, there are some other pressure gradient. Okay, but all those things are more or less the same concept, having the same concept. The production decline is also applicable for the oil, when you will see for the oil reservoir, but here in this case we are going to limit it for the gas reservoir. So everything which is discussed is this point of view of the coal bed methane reservoir. Okay. So the reservoir simulation is a very helpful tool, and at any point of time, suppose you are going to change your design and see that introduction of one borehole extra, or introduction to the one central borehole surrounding the one borehole, if you are going to put 4 other borehole in the 4 different corner, how your production is going to vary. So simulation is totally very versatile in its nature, and it is a constant upgradation of your production data. Okay, so the more and more you are going to change your initial parameter, change your design pattern, so obviously you are going to get more data, and so you are going to analyze furthermore about the sensitivity, about the importance of one or two or maybe a combination of the significant parameter and their effect on the gas production. Okay. So these are the different concepts. Now if you see the volumetric calculation, you have seen that you are going to understand the gas in place. Okay, so suppose that you are going to estimate the gas in place based on the reservoir data, and then you are going to identify the production, total coal production will be available. So only when you know that how much gas is available at that place, then only based on some recovery factor you will be able to get the production. Okay, so that's why in the summation they have provided in equation 3.8, you can see that reserves is GI, gas in place, of the initial reservoir conditions in 1000 standard cubic feet. M is 1000 standard, double M is the million, and the RF is the recovery factor. Okay, recovery factor obviously at the point of economic limit. If it is not cost effective, it is not economic, then you will not going for the production. Same as for the mining concept. Okay, so your total reserve, if you want to know the reserve, if you have estimated your total reserve, and then suppose in this case your total gas in place, and then you, depending on the initial gas in place with some recovery factor only, you will be able to know that this is my reserve in terms of gas production in that particular place. Okay, now the recovery factor, as you can see, you must have some idea about the core recovery in the rock mechanics class, as you know about the RQD. Now, if you read this, okay, read this text, they are going to calculate the recovering factor by three different prospects, by three different aspects, sorry, by three different aspects. What are the recovery factor you can use? The recovery factor is not easy thing, because it is very difficult to estimate the gas in place, and then again it is very difficult to calculate the gas recovery, because all the time, even if you are going to take the coal core sample and you are going to estimate the lost gas content, but there are some uncertainties, there are some lost gas which is already out, which is already elapsed, or which is already escaped to the atmosphere, and this is you cannot control. So suppose you are going to take, suppose 10 different sample from a particular reservoir area, you are going to do the disruption testing, and you are going to get 10 different results, but all are having some marginal error. Okay, so then you have to do the standard error technique, and you will be taking the mean volume of this gas in place. Okay, but then this gas in place, as we have seen earlier, that if the reservoir is not saturated totally at that particular pressure, your gas in place condition is again going to vary. If at a particular pressure, suppose at 500 meter depth, a gas CBM reservoir is gas content is having SCF, but okay, and the pressure is 1 megapascal. Now, at that 1 megapascal, you don't know that the gas whatever is stored, the gas content, what I have told, has 100 SCF per ton. It is totally saturated or undersaturated. This only you have to estimate. You can only tell whether it is totally saturated or not by taking out the pumping of the water. If by pumping of the water you are directly going to get gas production after some time, then you can assume that okay, as you are going to pumping out the water, the gas is totally coming out, so there is a chance that the gas pressure, that the whatever the reservoir is there, it is already gas saturated. If not, if it is not saturated, totally saturated, if the reservoir is partially saturated at that point of time, so that whatever the isotherm graph, as you can see in this graph also, the isotherm graph is lying above than the gas content, then obviously if you are going to reduce the pressure, it will not give rise to the gas production. Why? Because the reservoir pressure is much below that. Okay, the reservoir pressure has to go, then the initial reservoir pressure, and then the gases will dissolve, it will come out. So that pressure at the point where the gases will be started to dissolve, you have to reach that point from that reservoir pressure, from that initial reservoir pressure condition. And so the critical disruption pressure is the very important point. But you can only infer, it, you cannot fix it, because you are continuously taking out the water, so you can only estimate. Okay, so that is the only thing which will prove that the reservoir was totally saturated or how much saturation was there. If you know the gas saturation, if you know the initial gas in place, and if you can calculate the recovery factor by this formula, as you can see, the total recovery of the reservoir you are going to get from this isotherm graph. This is the critical disruption pressure. This is the initial gas content which is lying below the isotherm graph of that reservoir, and this is the isotherm established from the disruption canister testing, and then this is the abandonment pressure. So no low pressure is allowed. No gas production will be possible beyond that pressure. So then what is your recovery factor? This minus this divided by initial gas reservoir. So they are going to calculate as 76%, as you can see from here. So this is one of the technique you are going to get your recovery factor from the isotherm graph, okay, which is the easiest one based on your canister testing. The second factor is by the analogy. What are the analogy? And for the, and let me tell you, whenever you are going to get the recovery factor from isotherm graph, okay, there are some technique. There are three techniques. First is the calculate the recovery factor from the absorption isotherm graph by desorption testing or by the laboratory testing. Then it is the determine the recovery factor based on the analogy with the nearby producing wells. And then third is by the reservoir simulation. For each of these technique, which technique you are going to follow, that will be dictated by how much data you are having at that point of time. If you are having more data, then obviously you can directly go by the isotherm, you can directly go by the analogy, or we can go accurately measure by the reservoir simulation. If you are having very less number of data, then you have to go for the laboratory analysis, and then you have to go for isothermal analysis data. Okay. Next is the recovery from the analogy. What is the analogy? The recovery factor from the production method wells is by analogy with the nearby production wells. That means you know that what is the production well spacing, okay, and then if you are having some earlier data, if you have monitored the earlier data with time, how much gas production is coming, then you can see, you can take that data and with some other reservoir properties estimation, you will be able to get the recovery factor, because the main thing to estimate is the gas in place, initial gas reservoir place. And for that, you have to calculate, if you know the initial gas in place, then also you have to calculate the saturation factor. But saturation factor is very difficult to understand, as I mentioned. Okay, so what are the different assumptions should be taken? These other wells, the analogous wells, should be of sufficient maturity that their recovery can be estimated with accuracy. That means it is not there that the production has been just started. If you are going to take the other production data and you are going to integrate, you are going to acquire the data and you are going to use it for your production wells, you are going to forecast that recovery, then obviously you have to study some borehole data for which the production has been already started, and it is going to give the production in some regular fashion. Otherwise in the initial situation, you know that the production phase 1 and the phase 2, those are very short and the data is very much erratic. The water production is very high at constant rate, and then it is going to quickly it is going to down, okay, and the gas production is also not optimum. Gas production is reached, it is very less. So you have to take care. If you are going to consider the recovery, you have to come to you have to achieve the more or less constant or more or less the peak pressure limit, peak gas production rate. Otherwise it is of no use, because your recovery, otherwise it will be showing that it is very less recovery factor. Okay. Next is the well spacing. Well spacing of the analogous wells should be similar to that of the current development project. Suppose whatever earlier data you are going to consider for forecasting, if your earlier design and this design, there is a lot of variance. Suppose in the earlier design you have taken 100-meter difference for the borehole production wells, and here also you are also going to consider 100-meter or suppose 125-meter. Okay, a lot of minimum variation, but that doesn't mean that you are going to consider the data from 100-meter borehole and you are going to put the data, you are going to predict your design, which is in where you are going to put your boreholes at 500-meter depth, at 500-meter intervals. So then there will be some problem. Why? Because the conditions, the overlapping zone, the reservoir porosity, the reservoir permeability, the reservoir properties for doing the drilling, doing the impact of the drilling, okay, and the reservoir properties, the coal fractures, whatever is present in that case, in the earlier case, from where you are going to take the data. In this case, when the boreholes are 500 meter apart, the inside, the in-between point of these two boreholes may be quite different. It will be quite differently behaved than the earlier boreholes. In the earlier case, their zone of influence may be so less that this total, there may be an overlapping zone. Okay, so the fractures may have progressed, may have intersected between the two boreholes when you are keeping the boreholes spacing at 100 meter or suppose 125 meter. But in case of 500 meter, depending on the borehole data, depending on the borehole diameter, depending on its depth, depending on the depth of the your reservoir, there may not be any intersecting fractures present when you are going to put the 500 meter separation. So in that case, if there is a less number of fractures, so obviously your gas production is going to decrease, and so your recovery is also going to decrease, as you can understand. Okay, so whenever you are going to consider this recovery vector, you have to understand this design and these assumptions. Okay, the third one is the reservoir permeability. As just now I have mentioned, the reservoir permeability of the analogous reservoir and the current development reservoir should be of similar magnitude. If your fracture is not very much well intersected or very much well propagated or very much extent, the rock type is not that much the same, more or less same rock type, so obviously it will not be compared, and whatever data you will be getting by forecasting, it will be very much error. Okay, it will be having very much error. So for that thing, whether you are going to consider the well designed pattern, and whatever you are going to analyze from the other design or from this design, you have to check it. Okay, otherwise there will be a problem. Okay, you cannot compare the two different design or two very wide design boreholes, and you are going to tell that, okay, I'll be taking this other data and I'll be going to implement this in my observations or my project. No, it is not allowed. Okay, why this? Why you have to keep this in the mind? Because whatever borehole data you are going to study, suppose there are 10 CBM project in your area. Okay, suppose that in your state, suppose in Odisha, there are 10 CBM project, and suppose the 2 CBM project is already completed and 8 is going to still they are going to develop. Some of them has been started the production. So what you can do, you can take the other 2 data, and you may have the chances of estimation. You may generate some information that, okay, there are other 2 data, there are some different reservoir simulation, reservoir parameters, and so this was their technique. But then you have to check for your other 8 reservoir parameters and other borehole conditions. If not, you cannot totally input those data from the other 2 case studies which already completed into your data. That will be very much error in the, because the deposition in that 2 areas and the deposition in other 8 areas may not be actually the same, may not be actually having the same depth, same coal properties, same coal maturity, same coal composition, grade, everything can be different because it is natural process. Okay, and as the location changes, you know that there may be some chances of the impurities, there may be some chances of the low grade, there may be chances of the water accumulation, okay, or other chemical accumulation. So these things are going to be varied. So you need to think about those. The third is by the simulation. Simulation technique, just we have discussed that there are different parameters. You are going to choose some other borehole parameters. Suppose for this 10 number of boreholes, as I mentioned, you can have the data, you can see the data of the 2 different boreholes for which the production data you are having. So you are going to run this program, and then whatever data you are having, so now you are going to change the earlier data to suit your observation. Suppose in the earlier data you have taken that the borehole depth is 1 kilometer and the porosity, reservoir porosity, you have taken as the 10%. But now you can see that whatever the third borehole analysis you are going to estimate, the porosity is very high, porosity is 15%. So what you will do, you will take the earlier data, whatever initial data you are getting, Okay, suppose earlier porosity for the earlier two boreholes was only 10%. So now you will take this data and you will just change the porosity after comparing your reservoir properties. You will just change the reservoir porosity to 15% and run the simulation and see what are the other sensitive issues are coming, what the variations in the production are coming. But obviously you can only you have to check only one variable. Okay, I have told about the porosity. There may be some other variables, so you have to check whether the other variables are also coming to the same, more or less same constraints or not. Suppose if the locality is more or less same, then generally the rank is more or less remaining the same. The depth is not going to very much vary until unless there is a very fault, there is a fault or there is a very high incline fold. Otherwise the deposition is going to vary because it is sedimentary rock, and if it is nearly flat, so the depth or the beds, the lower bed and the upper beds of a coal methane reservoir are more or less the same. Okay, the fractures, the stress variations are also not going to change. Okay, because the stresses are going to change depending on the depth, depending on the discontinuities. Okay, so if there is a no discontinuity, so obviously the orientation, the direction of the principal stresses, okay, so that is also not going to change. So you have to compare this, and then only you are going to change one parameter of the other borehole of the earlier data and maintain and give the new parameter of your newly studied boreholes. Okay, suppose third borehole, and then you run on for each parameter. You have to run on the simulation and see how much the nature is going to change. Okay, and then you are going to estimate the recovery. If you see the data, if you see this data, suppose for this graph, okay, for this graph I have mentioned you earlier, like the ISM, how we are going to see the abandonment gas pressure, the recovery factor, the saturation. Okay, so this is also a very important graph to analyze the recovery factor. If we are going to see the simulation pattern, okay, in this graph they have shown the simulation how it is going to vary. So see, if we are going to do the production decline analysis, okay, or if we are going to the recovery factor, you can see the fluid system permeability is plotted with the recovery efficiency. Okay, original gas in place, percentage of the original gas in place. That means how much of the initial data, how much of the initial reservoir you are going to take out. And you can see with this is based on the function of the permeability and the fracture half length. So fracture half length means the persistence, the length of the permeability, the length of the fractures. So you can see that the skin is 0, that means it is very no permeability, it is skin is totally performed, skin is totally well, and then they are going to change the length with 100 feet to 800 feet. And as you can see, that if you are going to change the 100 feet to 800 feet, you are going to see the production is going to increase. This is the skin factor 0, then it is the LF at 100, then LF, third one is the LF at 200, LF at 400, and then LF at the 800 feet. So what this suggests, you can tell that at the end they are going to reach the optimum, or they are going to reach more or less constant production. Yeah, it is okay. With the permeability, they are going to reach a final production, but then at the changes in the initial condition, you can see it is the logarithmic graph. The permeability is going to vary in logarithmic fashion. So for a change of the fracture from 100 to 800 feet, okay, from 0, this is 100, from 0 to 800 feet, you can see that the permeability is going to change the order of 1. So if earlier it was 0, now it is 1. Okay, or maybe if earlier it was just going to be 0, now it is -1. So that means the change in the permeability is obviously going to change your recovery factor. So more permeable, obviously your gas production is going to increase. Okay, so here you can see the permeability is going to increase in the right side. So 0.01, 0.01, 10 to the minus 2 is 0.01 to 10 to the 3 to 1000 millidarcy. This graph is going to vary. And as you can see that your length, depending on the length, okay, depending on the length, the same permeability, okay, the same permeability fracture is going to give the production. Okay, so how this simulation is going to take place? So this is the product, this is the recovery. So if you are going to change only the fracture length, it will be going to change the production like this, recovery factor like this. Okay, in the second case, of the recovery, you can see they have changed the coal system permeability. Earlier it was the coal system permeability with the recovery factor, and here they are also taking the same parameter, but the difference is the design. What is the design? In the earlier case, simulated 20-year gas recovery as a function of the permeability and the fracture half length with 80-acre well spacing. This is the well spacing. Okay. In this case, you can see, second case, they have taken the same 20-year gas recovery as a function of the permeability and the fracture half length, but the well spacing is 160 acre. And the third case, the well spacing is 320 acre. Okay, so what is happening here? If you see the comparison, let me show you the graph in the same display. Yes, sorry, this is coming into the earlier and this phase. So if you see this, you can clearly see this production data, the permeability and the production data. Although the production data is going to vary from 0 to 80, the same y-axis, but the permeability is going to shift to the right side. As you can see, the permeability is going to shift in the right side. Okay, see the nature. Okay, you can see that in the last case, the 320 acre spacing, the permeability is going to increase more than 10. Okay, and the production graph is also going to vary. Okay, so what does it signify? It signifies that when you are going to change the well spacing, okay, you can see that the initial cases, you can see in the corresponding to the 80 acre well spacing, there is no horizontal line initial stage. That means the gas production is continuously increasing from the very initial point. In the second graph, you can see that at some point when the permeability is very less, it is the rate of increasing is much more less, and then continuously all of the graphs are parallel. Okay, whereas in third case, when the acre spacing, the 320 acre well spacing is there, you can see that the initial stages, the production is very less, the recovery is very less, and the rate is continuously changing at the initial cases. It is only after certain increasing of the permeability, the gas production rate is going to increase. Okay, so this is the effect of the well spacing. Okay, now is the production decline analysis. The production decline analysis means how we are going to integrate the data of one borehole reservoir to the other. Why this is important? Because the production data, observing this graph, it is going to give you with time, when you are going to study the production decline analysis, it is going to give you a lot of information, because at the continuously you are going to get with time, you are going to reduce the pressure, and the output is that production is happening. But it is not only a single parameter dependent production. With permeability, pressure is reduced with taking out the water, there are a lot of things are happening. Okay, for example, you know that the gases are going to dissolve. This is the first case. Again, as the absorption, during absorption, gases are going to absorb the gas, and coal is going to absorb the gas, and it is going to soil. The pore volume is supposed to go increasing by soiling. The opposite process during desorption, it is going to shrink because it is going to dissolve the gases. So shrinkage, if you are going to shrink, if you are going to imagine that the coal volume or the coal structure is going to shrink, what is happening? The pore volume is going to shrink, the fractures, okay, and what is happening to the fractures? If the solid coal matrix is going to shrink, the permeability is going to increase, because if the matrix is going to shrink, the fracture is remaining intact, because the fracture is the natural thing. Okay, so the fracture aperture is going to increase because the matrix volume is going to reduce in size as the production is going on. The pressure is going to reduce and the production is going to happen. So gases are going to dissolve from the coal pore volume. So the internal pore pressure is also going to reduce. So now whatever the earlier pore volume was swelled, now it is going to reduced and it is going to reach to the original pore volume space or the original pore volume magnitude. So what is happening? The solid pore volume is going to reduce. So if the pores are going to reduce in volume, what is happening? The intermolecular spaces or the intermolecular fracture spaces are going to increase. So now the fracture apertures are increasing, and so the production is going to affect. The production is also going to increase. Similarly, the permeability is also going to change at the same time because the fracture is going to increase, the aperture is going to increase, so the permeability is going to increase. As the permeability is going to increase, again the Q, the quantity flowing per second, is again going to increase from this fracture system. Because what is happening? Because Q is depending on the area and the volume. Okay, Q is the area into volume. Even if your velocity is same, sorry, area into velocity. Velocity is the same because the constant rate of production, the velocity is same, but the area is going to change in. The cleat surfaces are going to change. The cleat area, the total fracture area is going to change. So now the Q is going to change. Again, as the Q is going to change, the saturation, the relative permeability, the gas permeability, the water permeability, everything is going to affect now. So your production decline analysis you need to study because it will lot of parameters is going to change at the same point of time. So the more data you are having, the more information you are going to gather, the more it will help you to understand the storage and the production or the transport and its other limitation parameters. Okay. The decline analysis is also very much useful. Why? Because it is widely accepted and practiced technique in the conventional oil and the gas industry. Because by knowing only this, by getting this data, you will be able to do any type of simulation, because once you are having a basic accurate data, you can change those parameters, any one of the parameters, and you can get various results, and you can see the most significant parameters for particularly your reservoir, for particularly your design, for particularly your type of gas production. Okay. And second, it is relatively easy to use. It is very much easy to use because if you are getting only one data with time the production. So if you can see the other changes, okay, with time you are having, if you accurately get the production data, you can accurately change it for some particular analysis, for some porosity, permeability, other parameters, and you can also get that whether the production is going to increase or not. It requires only the well producing history. You need to have only this production data. So basic reservoir data, if it is available, your lot of trouble is going to end. Okay, so that's why it is performed. So what are the other things for this decline analysis? What are the things you need to assume? For decline curve analysis, okay, it is very much essential. It is essential that you have to have some initial data, and if you have this decline analysis graph, production graph, you can accurately forecast your other, you can accurately predict your other reservoir before you are going to go for the actual production. Okay. But there are certain criteria. What are the different criteria has to be met? You're decreasing gas and water rates. You have to have the total information about the decreasing gas and the water rates. That means with your particular reservoir property, with your particular reservoir gas production, what are the rate, whether you have continuously monitored or not. Okay. At what time they are going to reach the peak stress, peak rates. At what time the water saturation is going to reduce nearly 0% or 10%. At what point of time your water saturation and gas saturation are 50-50. This will give lot of output, lot of analysis for that. Okay. Consistent slope in gas rates for at least 6 months. This is very, very important. Why For 6 months, you need to have the consistent slope. If you are not going to have this consistent slope, you don't know that which one you need to take as an average slope. Okay, suppose you can see in this graph, that from zero to peak point, okay, from zero for this production well, from starting to the initial stage, you can see that a different rate is going to be observed. Then if you are going to maintain this different rate, you can see that as the parameter is going to change from 100 feet length to the 200 feet to the 400 feet. Dean office fast floor. Yes, if you are going to see the variation, the length of the fracture, as this fracture length is going to change, you can see the permeability is going to increase from 10 to the minus 1 to 10 to the 0. Okay, so with time, and you can see that the gases are going to, recovery factor is also going to improve. Why this? Because with starting, as you are going to get the water pressure, so obviously depending on the aperture, your permeability is going to change. So obviously for zero aperture, your rate is quite less, and the permeability and the gas rate is also starting from the zero. Whereas at the same time, with some high length fracture, it is not starting from the zero. It is starting from, at least you are from continuously from the beginning, you are going to get some recovery. Okay, and then you are going to maintain a more or less slope, constant slope, because this slope will be taken for your average production, and then it is going to stabilize, then it is going to decline. Okay, so if you are going to take the maximum slope or the average slope, then you have to take at least a consistent data. So that's why you have to go for the at least 6 month production data, so you can understand that what is the total data you are going to get, how much production you are going to analyze, because 6 months of the water or gas is totally coming out, and then only you will be able to predict having those data. Okay, length of the life greater than 22 months including 6 months period is the second criteria. That means whenever you are going for the decline curve analysis, you know that there are 3 phases. So these 3 phases, to study, to get these 3 phases, you have to have this life of a borehole should be more than 22 months. That means nearly 2 years. So your borehole should be continuously able to produce gases around 2 years. Okay, otherwise you will not be able to get this thing, and this is including of this continuous 6 month constant rate. Okay, next other criteria is that bounded wells and well spacing. That means what is the well boundary, that means the well spacing you have considered, and what are the well boundary, that means whether you have provided the casing, what are the rock stripes surrounding that well, the spacing are overlapping zone of influence or separate zone of influence, what is the rock strata, okay, what is the strength of the rock. So everything will be coming to the picture. And next is a redefined gas or liquid ratio threshold based on the field analogy. A well exceeding this threshold is interpreted as a bounded well. That means, as you know, that depending on the gas and water permeability, at all the time during the production, the relative permeability is going to change, and it is the relative permeability other than the actual absolute permeability of the individual gas and the water, they are going to dictate that in your production capacity, how much will be the water, how much will be the gas. Okay, you can also take in the saturation, like a production saturation in the production well, how much your production will be saturated with the water and how much it will be saturated with the gas. Okay, so if you see this table 3.9, they are going to give some parameter, and the concept of this parameter, what are the equations they are going to take. This is, I'm telling you, this is just to give you an idea to all of you. You don't need to remember all these equations, but you need to understand that how this relationship can be calculated and what are the effect of the parameter, how these equations, if you are going to change the equation from exponential to the hyperbolic, whether the parameter, the gas production is going to change or not, and what is the importance of this parameter. Okay. In the figure 3.19 also, you are going to see the material balance equation and the flow equation calculations, okay, their effect. So if you are going to see with time, they are going to provide the gas production analysis, okay. So here it is also giving me thousands standard cubic feet per month, okay, per month, in time is in month. So you can see it is a logarithmic graph in y-axis, and with time you can see that it is starting from the zero, increasing continuously. The way when the phase 2 has been started, the gas production is just continuously increasing very steeply, and then it is going to reach the peak point, and then it is going to decline again. So maybe you can, if you see the different months, then only you will be able to understand when it is going to saturate, when it is going to increase, and when it is going to start again declining. Otherwise, not. That's why it is always required that you should be having at least 2 years of data. Among them, only 6 months has to be a constant rate. Okay, so you can take that if this is your constant rate, see this 4 months, and then it is going down, and again this 4 months. So you can take that, okay, this is the your average slope of the gas production, okay, initially, and then this is the peak rate. This is your peak production graph. So again, you can see with time, okay, for the methane exploration or for the other gas production history, as you can see, you are going to get the line, you are going to get the prediction. So in the lower graph, figure 3.20, they have given some exponential fitting line, that if these are the initial data you are going to have, this production can be forecasted like this. It can be predicted that with these years you will be going to get like this, consideration of the other general properties. Okay, so this is the way we are going to get the production data. Okay, like that also in this graph 3.21, you can also see that although it is very less number of data initially, the history, this should not be done. That means you should be having ample data, a lot of data, so that your forecasting may be accurate. There is a most chances of error, there's a many chances of error in this production. Okay, so I stop here. If you are having any confusion, you can ask me any questions. Any question, anyone?